Okay, so we're very happy to have Joaquin Turiaci from IAS, who is going to talk to us about the SYK model. And welcome. It's a shame that you are not there in person, but that's life, I guess.
Yeah, thank you very much for the invitation. And yeah, hopefully sometime in the future, I can be there in person sometime. But yeah, so I will be talking about phases of n equals 2 SYK models, and it's based on a paper with Matt Heidemann and Wenli Zhao that should appear sometime soon. Okay, so let me give a couple of motivations first. Let me put this like this. Can you see it?
Mm-hmm. Yes.
Okay. So complex SYK is an interesting quantum mechanical model that displays features that are similar to black holes. And this model was introduced by, some version of this model was introduced by Sachdev-Ye and then by Kitaev, and in particular studied in a lot of detail in this recent paper. And it's a model of n complex fermions, quantum mechanical model. And fermions interact in its simpler version via this four-fermion interaction that preserves some U1 symmetry. And this matrix of coupling constants is in principle random, and it's usually taken from a Gaussian ensemble with a variance given by this expression here. So then the model depends on this dimension full parameter J and the number of fermions. This model develops an immersion conformal symmetry at low temperatures, and that's why it's interesting for holography, because it's believed to be dual to some theory of gravity in ADS2. And in particular, it can be studied at non-zero charge because there is some U1 here. And that corresponds to turning on some electric field in ADS2. Moreover, this model displays maximal chaos, which was one of the original motivations from the holography side for studying it. It's compressible, which means that one can change the charge by changing the chemical potential. And it has a large zero temperature entropy. In the gravity perspective, this zero temperature entropy corresponds to the extremal. If this ADS2 appears from some near extremal black hole, then this is like the extremal entropy. In some kind of recent papers by these authors, it was realized that even though this picture is correct at zero charge, as one turns on the charge, there can be phase transitions to low entropy phases that are gapped and do not have any immersion conformal symmetry. And this is kind of, well, this was analyzed numerically, but it's kind of mysterious from the perspective of the conformal solution because there is nothing that goes wrong. So one motivation could be to try to understand these phase transitions a little better. This will become clear probably if you're not familiar with it later when I will give more details. Okay. Now, I'm not going to have much to say about complex SYK, but there is a deceptively simple modification that takes the random couplings, this 4-index metric to be given in terms of. So before I was taking it to be a random variable with Gaussian statistics, but one can take a different ensemble. And for example, take it to be given by a complex matrix C, and then J is the product of C bar C, where C has 3 indices and one sums over some intermediate indices. And now it's this complex matrix C that has some Gaussian statistics. So this is a different model. And this has drastic consequences in the behavior of the model. For example, it develops n equals 2 supersymmetry with a supercharge given by this combination of fermions. Then the Hamiltonian is naturally given by the QQ bar anticommutator. And this model was introduced in this paper by these authors, and it was shown to develop a superconformal symmetry in the IR with the group SU1,1/1. And this is basically a superconformal group that includes the bosonic conformal group SL2R and some U1 R symmetry plus some fermions. And what we are going to do in this talk is to study these phase transitions in this particular model and at non-zero charge, and we will find that they have a simple interpretation as opposed to the case of complex SYK. As a separate motivation, the model of this paper of Fu et al. Has fractional arc-charge fermion. What that means is that because this supercharge is given by a product of several fermions, in units in which this arc-charge has, the supercharge has charge 1, the fundamental fermions have fractional charge. For example, we'll see these models have vanishing Witten index, but they still have a large ground state degeneracy. This is not the behavior that happens in black holes in higher dimensions, where usually the fundamental charge is related to the charge of the supercharge, and also they have non-vanishing index, they have a large ground state degeneracy. So in the second part of the talk, I will construct some generalization of these models that behave a little closer to black holes in higher dimensions. For example, this near 116 BPS black hole in ADS5. And well, if you're interested, you can see Matt's talk next week, I think, next week or the other. Okay, is there any question about the motivations?
Can you explain why the fractional arc charge implies that the index vanishes? Is it obvious?
Yeah, that should. I will talk about it later. So you can ask me again, maybe if I don't say it. Yeah, but we will see it in the details of the solution of the model, how it comes out. But basically, what happens is that the ground states, when you have these models of fractional charge, the ground state come with a spectrum of arc charges, and it happens to be that they always cancel when you compute indices. Well, if you have a model where you don't have fractional charge, usually the ground state comes with only 1, basically with 0 arc charge. And then the degeneracy is the same as the index. But yeah. Okay, so now I will go into the details. So let me introduce a little more detail this n equals 2 SYK model. As I said, it's a system of n complex fermions will satisfy these commutation relations. The Hamiltonian is given by the anti-commutator of the charge if we have n equals 2 supersymmetry. And we will generalize the model to include a product of Q fermions in the supercharge. And then we have this coupling constant matrix that has Gaussian statistics, and the variance is characterized by this dimension full coupling J. So the theory has a U1R symmetry, and it's generated by this generator. So this is one that gives the fermions charge 1, but the R charge, which we define such that the supercharge has charge 1, has a 1 over Q. So then in the case with Q equals 3 that I showed before, then the fundamental fermions will have charge 1/3. So they're fractional with respect to this QR. And if n is odd, then the charge is half integer because of this n over 2. Well, that's related to something I can, someone interested, I can say, but it's not too important. But I should mention that this n over 2 is put there so that this is the spectrum is charge conjugation invariant. Okay, so the first thing you can do with supersymmetric theory is to compute the index. The fermion number is this -1 to the f. We can write it as e to the I pi QR, so that states that are not preserved by the supersymmetry are they cancel when one takes the trace. Now the index of this theory always vanishes. The trace of -1 to the f is 0, and this can be easily computed in the free fermion limit. Basically, if you have n free fermions, you can look at what happens for one fermion, and then for one fermion you either have the fermion or you don't. You either act with the fermions or you don't, and they come with a minus sign because of the -1 to the f, so the index vanishes. So one can ask if supersymmetry is broken, but the answer is no. There is still a large number of BPS ground states, and one can see this by computing a refined index. So what this index is that, so if you look at the supercharge, there is still a discrete CQ symmetry that commutes with the supercharge, where all the fermions are rotated by the qth root of unity, basically. So basically, they're rotated by a phase such that when you take the product of the Q fermions, it gives you 1. And this is what this insertion is doing. This is just including a chemical potential for this discrete symmetry. And one can compute the index refined index for this discrete symmetry, and this was computed in the paper of Fu et al. And well, now the difference between acting or not with the fermion is not a minus sign, but there is some phase, and the index is actually given by this formula. So here the sign of pi r over q is just the difference between this discrete charge of the whether you act with the fermion or not. If you maximize this with respect to this discrete chemical potential R, then there is maximized for some values, and the maximum of the index is given by this expression. So at large n is exponential with n, and one can actually see that this is also the number of ground states of the model. So we will reproduce this number in a different way later. So okay, so this indicates that there is still a large number of ground states, and supersymmetry is unbroken. Okay, so now we want to solve this model at strong coupling or equivalently at low temperatures. For simplicity, let me focus on Q equals 3. So to derive the mean field theory, so we're going to use the same procedure as for complex SYK. We will derive a Schwinger-Dyson equations that can be solved. Now, in order to do this, it's necessary to introduce an auxiliary boson so that supersymmetry can be realized linearly. Right now, it's realized non-linearly, and if Q acts on psi, then you get some non-linear combination of fermions. But you can define this to be a boson and integrate it in. And then you can write your theory in superspace, where these coordinates Z, that is tau, and theta and theta bar are the superspace coordinates. And the fermion with this auxiliary boson can be packed in a chiral superfield written this way. So this is the fermion and this is the boson. And then the action is very simple. So this is the free fermion action that gives you the free fermion. Sorry, this is the free chiral superfield action. So this gives you the free fermion action and the action of this boson. It's important, and this is this has no time derivatives, and the reason is that this is basically integrated in as a kind of using the Haber-Stratonovich trick. That's why it appears with no derivatives. And then the interaction is written in this way, just the product of these chiral fields. When you write it in components, you get basically you have to replace one of these superfield psi's by one of the bosons. You get this. And when you integrate out this B, you get the theory that I wrote before. Okay. So now we follow the usual tricks of SYK, and we introduce a bilocal 2-point function. So this is a 2-point function of these chiral superfields. So this is a bilocal function that is anti-chiral on the first variable and chiral on the second, because this is a psi bar. And similarly, the self-energies. From this superfield, you can read off the correlators between two fermions, between two bosons, and between a fermion and a boson. In this is just to show you that there is a formula, but the details are not too important. So the procedure that one uses to solve the theory is that one first introduces this bilocal, and the self-energy sigma is introduced as a Lagrange multiplier that enforces this condition. Once you do that, then you can integrate out the disorder and also integrate out the fundamental fermion, because basically the action becomes quadratic. And one ends up with a mean field action that happens that is and one can read off the equations of motions for these correlators. So this, I'm not giving too much detail, but you can ask me, but this is what everyone does in this type of models. And the equations that one gets are the Schwinger-Dyson equations that one can also derive by diagrammatical techniques. So this equation relates the self-energy to the 2-point function in this way. And then one can solve for the 2-point function using the lower equation. But okay, this is a very complicated equation. It looks nice in superspace, but if you start writing in components, it's kind of a mess. But a strong coupling, as I said, because the coupling is dimensionful, strong coupling corresponds to low temperatures, and in that limit we can basically ignore this term that comes from the free fermion part. And this equation will be easier to solve than the full one. And this is where the conformal ansatz appear. Okay, so now we're going to solve the equations in this limit. So first of all, we can consider a solution where the fermionic correlators vanish, and that has time translation invariance. Then if you write the equations I showed in the previous slide more explicitly, you have these 4 equations. So these are the one that determines sigma as a function of g's, and this one determines g if you replace sigma by the correlator. So here you can see that if you remove the self-energy, then you get the free fermion answer. But okay, so we will solve this in the IR where temperature is low or times are large, and the terms that we will ignore in that limit is this one and this one. And then we can put the conformal ansatz that is given by these 2 equations here. So you can see this, well, this lowercase g are just numbers, they're just coefficients. The dependence on time is just a power law with some scaling dimension. This delta is the scaling dimension of the fermion. This is delta B is the scaling dimension of the boson. And this theta is the illustrates the fact that when you turn on a chemical potential, the 2-point function for positive times doesn't have to be the same as the one for negative times. So that is quantified by this parameter E, that is a spectral asymmetry. It's called the spectral asymmetry. And as I said, this corresponds to turning on a background U1 charge. I will show the relation between the two in a bit. And similarly, you can turn on a spectral asymmetry for the boson. That will also be related to turning on the 1 charge. Okay, so the way to solve these equations is to start with the ones in the second line that are that G sigma is 1 in Fourier space. So this is like, for example, you take this equation and you forget about this one, or you forget about these terms, and you have that G sigma is 1 in Fourier space. This omega is the Fourier coordinates when you Fourier transform in time. So when we plug in the conformal ansatz, we can solve for sigma through these equations, and we get these expressions. And now to complete the solution, we need to insert these expressions for sigma in the first 2 equations. So basically, we have independent equation for sigma. So we put it in this equation, for example. We insert these expressions for G here. We insert the one for sigma here. And then we ask that this equation is satisfied. And that usually determines the coefficients, the scaling dimensions, and the spectral asymmetries in complex SYK, for example. But in our case, it's a little weaker. It imposes, well, first of all, it relates the bosonic spectral asymmetry with the fermionic one by this relation. And one way to interpret this equation is just telling you that on shell B, if you remember, is a product of Q minus 1 fermions. So this equation just tells you that the charge of B is Q minus 1 times the charge of the fermion. And then from matching the time dependence, you get a relation for the scaling dimensions, delta and delta B. And the scaling dimension as opposed to SYK is not determined by dimensional analysis. And the only thing you know is how to relate these two. But this is determined by looking at the prefactors. So then we need to ask that the prefactors in the left and right-hand side of the equations are consistent. And there is something special of this model, which is that the 2 equations give the same. They give 2 different equations for the same combination of prefactors. G psi psi and GBB in this way. So then for the equation to be solvable, you need to combine these 2. You need to ask that these 2 equations are consistent. This is this equation below where I replace delta B by delta and to write everything in terms of the fermion dimension. And then solving this complicated equation gives you the fermion scaling dimension as a function of the spectral asymmetry. Now, as this means that the conformal solution is not fully determined, only this combination, but not, for example, the ratio between the two. That's not determined by the conformal solution. And I will come back to that later. Is there any question about this? Maybe before I move on. Okay, then we're going to look for superconformal solutions. And this happens whenever the spectral asymmetry is given by IR over Q, where R is an integer. In this case, the scaling dimension of the fermion is plus 1/2, gives you the scaling dimension of the boson by supersymmetry. Basically comes from this relation. And now we can find the full solution, because this relation also implies that the fermion, the boson prefactor has to be related with the fermion prefactor of the correlator. For simplicity, we can focus on R equals 0, which corresponds to 0 U1 archers.
Sorry, Joaquin. So how did you get that the spectral asymmetry for supersymmetric solutions is IR over Q? I mean, where did that come from?
So supersymmetry tells you some relation between bosons and fermions, that is this one. And this implies that delta and delta B has been, sorry, it implies that delta B has to be delta plus 1/2, because you take a derivative extra, okay, right? And then you go to this nasty equation and you ask for what values of E, sorry, then you go to this equation, sorry. This equation tells you that if delta B is delta plus 1/2, then delta is 1 over 2Q.
Okay.
Well, you can check it. Just replace delta B by delta plus 1/2. And then you go to this equation and you ask for what values of E delta is equal to 1 over 2Q.
Okay.
And that's where this number comes from. Then you get a discrete set of solutions given by this.
Okay.
And the interpretation is that issues correspond to turning on this discrete group that commutes with supersymmetry.
Thanks.
Yeah, so it's just combining different parts of the solution. Yeah. Is it clear?
I think so. Yeah. Thanks.
Yeah. Okay. But yeah, it all comes from here, and then seeing what are the implications of this relation. But okay, but let's take for simplicity R equals 0, and then at this point the solution has an emergent superconformal symmetry given by SL2R and U1. At least that's the bosonic subgroups. This can be written in superspace in this way. So the SL2R comes from, well, sorry, this has a, yeah. The equations have a bigger symmetry, which is the diffeomorphisms of the circle. So this is this reparametrization mode F of tau. And we also have this U1 mode A of tau that depends on tau, and some fermionic mode. These are all the symmetries that are preserved by the equation, but the solution preserves only this superconformal group. The way the correlators transform under these super parametrizations is in this way, where maybe it's not too transparent, but if you write it in components, then you can see that this acts as a reparametrization and this acts as a U1 mode. And if you ask what subgroup of this is preserved by the solution we just found, then it's this superconformal group. Yeah. Okay. And this is where you can start seeing some holographic interpretation, because you have something that could potentially be described by ADS2. Okay, so so we found that the full superconformal, the full solution of the Schwinger-Dyson equation is not determined by the IR in the IR. So what we did was to solve the equations numerically at non-zero charge, at any charge. So basically we plugged these 4 equations in a computer and solved them numerically. So there are 2 features I want to emphasize. Well, first, we can compute the scaling dimension of the conformal solution as a function of the spectral asymmetry. And we already see something funny, which is that the scaling dimension goes to 0 at some critical spectral asymmetry given by this number. So this is already hinting that there should be some instability as you turn on the charge. The upshot of this will be that this is a simple interpretation of this phase transition that I mentioned in complex SYK. The simplification in n equals 2 is that the fundamental fermion itself is becoming unstable as you turn on the charge. But okay, before I go on there, let me show in the right you can see the plots for the correlators, the GIP psi, the GBBs, and the dotted and dashed lines are the conformal solutions. From left to right, we are increasing J, so we are increasing the coupling. And above you have the solution at 0 spectral asymmetry, and below you have the solution at non-zero spectral asymmetry. In both plots, you can see that as you move to the right, the conformal solution approaches more and more to the exact solution. And the region where the solutions differ becomes smaller and smaller because that's the solution is only supposed to work in the IR, but in the UV, where time separations are of order of 1 over J, the difference is supposed to be visible, but as J increases, this region becomes more and smaller. So here we see that we can check that all the solutions make sense. There are actual solutions of the mean field equations. Moreover, we also check that the UV behavior fix this undetermined coefficient. So I said that this ratio of coefficients is not fixed by the conformal solution. But once you solve the equation exactly, then the UV determines some value for them. And this is the concrete curve that we get of how it behaves with epsilon, with E, sorry. So at 0 E, you cannot see it here, but this value would be consistent with the supersymmetric solution. But then as you turn on the U1R charge, then you break supersymmetry and then the solution can be different.
So you had these these points where you had supersymmetry for spectral asymmetry equals R over Q, but here it should be like 1/3, which is above.
No, sorry. There is a knife here, but I'm looking at.
There's a knife.
Yeah. So this is analogous to. Sorry, if I go back to the index, here I'm turning an imaginary chemical potential. Oops. Because there is an I here. Okay. So, but here I'm looking at real spectral symmetry. Yeah. Okay. So you wouldn't see it. Here I'm turning on a real chemical potential. Thanks. Okay. Okay. So. Okay, let me now move on to the following question. So I've been turning on this spectral asymmetry and saying that it's related to turning on the charge, but then you might want to know exactly how these two quantities are related. And this is given by the Latinger word relation. And this gives the charge expectation value in terms of the spectral asymmetry. And I think the first version of it for this type of models was derived by these people in 2000s. And this is an interesting relation because it relates a UV quantity, which is the charge, and the charge is a UV quantity because it's some 2-point function at equal times. So it has contributions from all frequencies, and it relates it to the spectral asymmetry that is something defined in the IR purely. It's just you need to look at the long times and look at the conformal solution and read it off from there. So it's kind of surprising that there is such a relation at all, but okay. And we derived this relation for this n equals 2 SYK, and we got this formula, this ugly formula, but okay, it is what it is. So this is the charge over n. This is the UV part of the equation, and then the right-hand side is the IR part of the equation. It looks ugly, but it has a simple structure. So, oops, this term depends on the Fermion scaling dimension and the Fermion spectral asymmetry, and it's exactly the same as in complex SYK. So if you go to that paper I mentioned, then you can find the derivation. Okay, so this is the Fermion contribution. And then we get another contribution that is from the auxiliary boson. this Q minus 1 should be multiplying the whole thing, but okay. So if you see it is very similar to the Fermion, where we replace the scaling dimensions by the boson ones and the spectral asymmetry by the boson ones. And this cosine is replaced by sine, but that's the only difference. And so this is interesting because even though the charge comes from the Fermion correlator only, so the charge is a Fermion charge. There is no such thing as the boson charge. Still gets contributions from the boson. So that's very different than previous cases in the literature. But okay, so then one can verify this equation numerically just to make sure. And so this is the plot. So the blue dots are the numerical evaluation of Q and E, and the black line is this formula. So one can see that it matches pretty well. But the important lesson from this is that this critical spectral asymmetry that we computed, to make sure that it corresponds to a phase transition, we want to check that it corresponds to a non-maximal charge. So there is a maximal charge that is n over 2, because you cannot well, the Hilbert space, you cannot act with the fermions more than once, right? But for this critical spectral asymmetry, the critical charge is less than maximal. So this means that this is really there should really be a phase transition as you go above this critical charge. And it's not that you run out of fermions. Okay. Okay, before I say some comments about the phase transition, let me say that, so we have an emergent super parametrization symmetry preserving the super conformal group. So this means that at low temperatures we expect there to be a Schwarzschian mode, because coming from the breaking of this super conformal symmetry is explicitly broken. There is no symmetry in this model that is conformal, and the Schwarzschian mode is this. You can think of it as the Goldstone mode of this broken symmetry. So it gives an action basically to this reparametrization mode F and the U1 mode A. So the reparametrization mode corresponds to fluctuations in energy, and A corresponds to fluctuation in charge. And this Q appears because of the fractional charge. So it tells you that the free energy, the free energy behaves linearly with temperature. So this is the zero temperature entropy. And then there is a term linear in temperature, and the Schwarzschian coupling, this alpha S, appears precisely in this linear term. And okay, we computed it numerically. This is not something that you can see from the conformal solution, because you need to break the conformal symmetry. So we computed this coupling, and then we check that, well, because of supersymmetry, this coupling has to be related to the U1 coupling. So you see that these two comes with a determined prefactor between them. And okay, we check that. So this the coupling of the U1 controls the compressibility, which is dq dmu at zero temperature, and these two numbers are related in the correct way to dictated by supersymmetry. So that we just good to double check. And furthermore, you can ask, what is the BPS spectrum of the Schwarzschian theory at the quantum level? And this maybe will answer the question of the index that were raised before. So if you solve this Schwarzschian theory that controls the spectrum at strong coupling, you'll get a BPS part and a non-BPS. The non-BPS is separated by a gap, and we don't care for the purpose of what I want to say now. And this is the BPS part that comes with zero energy, so you see it's independent of temperature, but it comes with certain charge distribution. So you see here that I'm writing as a function of mu. So charges are integer. The only charges that contribute to the BPS part are smaller than Q over 2. So for example, in Q equals 3 SYK, it would be only 0 or plus or minus 1/3 that could contribute to the BPS sector. Well, there is something interesting, but maybe I will skip it. It's interesting that you can look at the exact degeneracies of the BPS sector by exact diagonalization. That was done in the paper I mentioned in the beginning. And the Schwarzschian answer happens to exactly match, except for this one, it matches all the other numbers. So there seems to be something exact about the Schwarzschian description of these states. And maybe it hints that it can be a good setup to understand better the microstates of these BPS black holes from gravity. And there's some work in progress by Lin, Maldacena, Rosenberg, and Shan that's very interesting. But okay, all that was about the conformal solution. So now we can look at what happens as we go above the critical charge. As we go above the critical charge, I said that the claim that the solution develops a gap. So we can see it in this left panel. So this is G as a function of tau. So we see it decays exponentially, and this is a log plot. So you can see it's almost linear. And it also a transition between high entropy. So this is the conformal solution. And the transition happens here where it goes to zero entropy. And this is entropy in the large N limit. So it's high entropy means that the ground state entropy over N is finite. Zero entropy means that the entropy does not scale with N. So it has the same physics as the transition I mentioned in complex SYK, just that at least we understand it, I think, much better. Or there is a very clear signal in the conformal solution of why such a transition should appear. Okay, finally, for this model, we also look at the spectrum of bilinear operators. So this is the spectrum. Well, basically, the way to read this plot is that whenever a line crosses the real axis, then it means that there is an operator in the theory with that scaling dimension. So for example, at E equals 0, we find two sets of states with H equals 1, 3/2, and 2. And this is the Schwarzschian multiplet. 2 is the one that corresponds to reparametrizations, 3/2 to this fermionic part of them, and 1 to this U1 mode. As we turn on E, which means that we turn on a U1R charge, the supersymmetry is broken. And for example, the fermions are not at 3/2 anymore. They are a little separated. And suggests that one ends up with just the bosonic Schwarzschian with the bosonic U1 with some massive fermions. And then when we turn on the epsilon E above the critical one, there are complex solutions, which means that there are some bosonic bilinear modes that have complex scaling dimensions, and there is also a continuum of real ones. So basically, we see that everything goes wrong with this model, with the conformal solution of these models at these charges. Okay. Okay, so I was hinting a bit at the holographic interpretation of this. I would just make some brief comments. So one can give two pictures. One picture is that we have a theory in ADS2 with a U1 field. This theory that, well, if you ask what theory of gravity gives you this N equals 2 Schwarzschian, is N equals 2 Sachdev-Ye-Kitaev gravity coupled to Fermion multiplets. So this is the theory that should be dual roughly to this N equals 2 SYK. And as you turn on the electric field, what's going on is that the fermion becomes unstable. And this is not too unfamiliar, because if you look at the scaling dimension of a fermion in ADS2, which is this, well, here we put with Neumann boundary conditions for this minus, but that's not too important. You can see that if you turn on the electric field, then the thing in the square root can become complex. And what this is telling you is just that there is a non-zero probability of Schwinger pair producing fermions in that electric field, and then the black hole will become unstable. So that seems to be roughly what's going on with the dual of N equals 2 SYK. And the second picture is that gravity is emergent. So this is a very different holographic interpretation that is completely unrelated to the first one, that maybe the first one is more familiar. In the second one, there is something funny that was pointed out in this paper, which is that if you take fermions in ADS2 without gravity, and you compute their partition functions, then you can reproduce a lot of the behaviors of SYK, in particular the zero temperature potentials, from this bulk picture without gravity. So unfortunately, I don't have time to go into much details, but I can tell you if you're interested. But the only thing I can say is that it happens to be a nice way to find analytic formulas for SYK, regardless of where you think that this is a good way to think about it or not. So we applied a similar thing for n equals 2, and we found this formula for the grand potential. So this depends on deltas and e's. And so here we check that that formula is correct. So it matches with the blue dots again are the numerical calculations. And there is something interesting here, which is that if you ask what is the value of the fermion mass or the fermion scaling dimension that maximizes the grand potential, you're going to get exactly the equation I showed before that determines the scaling dimension as a function of the spectral asymmetry. So basically, if you vary this formula with respect to delta and you set it to 0, you'll get this. Where is it? This formula. Okay. So the next topic will be these new models that I will discuss. Is there any question about the previous one?
Do you have any analytic understanding of this critical value for the charge? Or...
Oh yeah, I wrote the form. Yeah, sorry. Yeah, I wrote the number here, but you can derive it analytically. Is wherever delta goes to 0. Okay. You just need to go to the formula from the conformal solution and ask what is the value for E where delta becomes 0, and then you'll find this some formula. Yeah, I didn't write it, but yeah, you can find it analytically. So but the surprising thing is that, yeah, sir.
If you go over this value, then the theory becomes gapped, or what's happening exactly?
Yeah. Yeah, I mean, above that value, you cannot really talk about spectral asymmetry because that's something defined through the conformal solution. So but then you can compute the charge.
Supersymmetry is broken above that value, or it's still it's gapped.
Supersymmetry is broken for any E.
No.
Because you're turning on the U1 charge, the U1R charge.
Okay.
So we are as if we turn on E, we are breaking supersymmetry. So all this is not supersymmetric solutions. So yeah, so you turn on the charge. So think of this as turning on the U1 charge. Then at 0 charge you have supersymmetry. Then you turn it on and you break supersymmetry, but you still have a conformal solution. And then at some point you turn it on so much that even the conformal solution breaks down and you go to a gapped phase. Yeah.
I think this chart operator commuted with the supercharge. That's why we could define this refine index. No?
Oh, no. It's only for a particular value of, sorry.
Only for discrete values.
Only for discrete imaginary values.
Okay, so it's okay. Once again, the same confusion as before. Yes. Okay.
Yeah. Sorry. Sorry. Yeah. This R is an imaginary chemical potential. Yeah. And it's only some discrete values. Yeah. Sorry. Yeah.
Thanks.
Okay. Any other question before I move on to the next model? Okay, so okay, I will try to. I will have to skip some things, but okay, I will try to be quick with one. Yeah, so as I said, there are a couple of motivations to generalizing these models. For example, we don't like, well, okay, whether you like it or not is, well, whatever. you might not be, if you're trying to construct a model that behaves similar to these black holes in higher dimensions, then you might not like to have this fractional charge, and also the fact that the index vanishes and all that. So the purpose of these models is to solve this. So a simple solution is to consider a model with multiple fermions, psi and chi. Then the Hamiltonian, we can write it in terms of the supercharge by this expression, psi chi. Then if you see this, there are two U1 symmetries for psi and chi. The important thing here is that the R charge is given by the charge of this chi fermion, and there's only one of them. So that means that it will lead to a model where the R charge of the supercharge is the same as the Fermion one, fundamental Fermion one. But there is something extra of this model, which is that there is a special role played by a flavor symmetry that commutes with the supercharge given by this combination of psi's and chi's. So if you rotate psi and you rotate chi in the opposite way with twice the charge, then this leaves the supercharge invariant, right? So this is a flavor symmetry that commutes with the supercharge. Well, as I said, there will be an emergent SU111 symmetry in the IR, conformal phase. And now there is an extra complication that the superconformal R symmetry is given by the chi charge, but is given by an undetermined linear combination with this flavor charge. And then part of the solution has to be to determine what this parameter alpha is. But up to that, the R charge is the same as the charge of this chi Fermi. For example, we can see, we can compute the index of the model. So now the Fermion number of the theory is given by e to the I pi chi. And I put Fermion in quotation marks because it has no contribution from cube psi. And that happens because there are two psi's in the supercharge. So if you have a state and you act on it with Q, it doesn't change the number of psi fermions modulo 2. So it's the only one that affects the -1 to. If you want to insert an operator that would cancel different states in a supermultiplet, it will have to be only chi. That's what I'm trying to say. But now you can insert, besides this -1 to the F, you can also insert the chemical potential for this flavor symmetry. Now you get this expression. And now if you go to a theory where you fix QF, you go to some fixed QF sector, now the index is non-vanishing. So the index is given by the Fourier transform of this grand canonical index. For example, you can do it for QF equals 0, then you'll get something that grows exponentially with S now. So this will be important in a couple of slides, but you can ask for when QF is 0, what is the saddle point for this in Fourier transform over Y? And it satisfies this this equation. YC is the point that maximizes this grand canonical index. And the expression for this S naught is given by this in Larsen. Okay, so the strong coupling limit can be solved in a similar way. You introduce chiral superfields psi and X here I call. X includes chi and their bosonic partners. The interaction includes now this psi X term, and one derives Schwinger-Leitzen equations for these both superfields psi and chi. That's all the same. Now one has four. They're just double the number of equations as before. So, but we will look at solutions where the Fermion correlators vanish and are translation invariant, and now we have to solve these equations. But again, we insert the conformal ansatz. This is all the same as before, just we have 2 copies of it, and the equations are more complicated. Just like before, we find the boson spectral asymmetries in terms of the Fermion ones, and this you can interpret as being related to on shell what are the charges of these bosons. So here you have Q minus 2 psi, here you have Q minus 2 e psi, e chi, etc. And this makes sense because you end up with only 2 free parameters, e psi and e chi, and correspond to the background psi and chi charge. And the scaling dimensions constraint gives you these 2 relations. So you can use these 2 relations to determine the bosons scaling dimension in terms of the Fermion. But now there are 2 unknowns, which are the 2 Fermion scaling dimensions as functions of the 2 spectral asymmetries. And again, the 4 equations I wrote before determine only 2 prefactors, and there are also a larger number of prefactors that are undetermined. But we will assume that just like before, the UV will pick some value for them. So again, we can find supersymmetric solutions. they impose further constraints coming from this relation on the scaling dimensions and spectral asymmetries. And now there is a one parameter family of solutions. And that corresponds to that one parameter which is turning on this QF charge that doesn't break supersymmetry. And for simplicity, take ip psi to be 0. This corresponds to setting QF equals 0. And then you find these simpler equations for the Fermion scaling dimension, psi. And this S naught is the ground state entropy. Now, the nice thing is that this equation for delta happens to be the same as the maximal value of the QF chemical potential up to this factor of 2 pi in the extremization of the index. Moreover, once you put this value of YC here, then you'll get that the ground state entropy is the same as the one that we derive from maximizing the index, extremizing the index. But okay, we will come back to it in a few minutes. Before I do that, let me go on. So these are we found super conformal solutions for some values of the charge. These solutions have a super parametrization symmetry. So this is just 2 copies of what we had before for n equals 2. But the important thing here is that now we can answer the question of what is the super conformal R symmetry, because we know how the fermions transform, and they basically transform as primaries of the super conformal symmetry. And that means that the R charge of the fermion has to be twice its scaling dimension of both fermions. Because we know what the scaling dimension is through the Schwinger-Dyson equations, we can determine the super conformal, the R symmetry in this way. So before we had alpha, now we can determine that alpha is equal to twice the scaling dimension of psi. So this determines what the R symmetry in the IR is. And again, we can see that the R charge of the supercharge is 1. So this will lead to the simplest Schwarzschian theory that now will include only QR equals 0 ground states, and the index will be equal to the degeneracy. So just to elaborate on this a little more, so this is consistent with the idea of index maximization that I think it was proposed by these people in the context of black holes in ADS4. So this is the answer to the question of why does the fermion dimension match with the value of the chemical potential that extremizes the index. So the idea is that you define an R symmetry that is some trial 1 plus alpha F, and then alpha is obtained by maximizing the trace of e to the I pi R. So if you insert this here, you'll see that alpha will appear as a chemical potential for F, and that's exactly what we called Y before. So, basically we saw from the exact solution of the model that the index maximization is correct. And this is very different from the case studied here, because the case they studied correspond to an exact superconformal quantum mechanics. And I'm not sure I know what a superconformal quantum mechanics is. Instead, I think the thing that is better defined are nearly superconformal theories in one dimension. And these are theories where the conformal symmetry is broken by small effects. So it's nice to see that this principle still works in this context that I think is a little bit more relevant even to the black holes that they studied. But of course, it was before all this was understood. But as far as I know, there is no proof of this. So it would be interesting to understand why this happens, and if we can extract maybe some information about other theories that maybe we cannot solve exactly in the IR as we can for SYK. But okay, and last comment is that this index maximization statement, besides saying that you can determine alpha this way, it also says that the maximal value of the index matches with the ground state entropy. And that's also something else we found because of the fact that, that we just checked from the exact solution. Okay. So this is just okay, this I can skip. So this is just the Schwarzschian theory. So before there was a Q square, but now that Q is 1 because we don't have fractional charges. And now the quantum Schwarzschian spectrum of this model is just this. So if you remember before, there was a sum over charges here that was responsible for the index canceling, but now it's just one state. And this is the Schwarzschian theory that appears in the near VPS limit of black holes in ADS5 with non-fractional charge. And I think probably this is what Matt will explain next week. Okay, finally, let me mention quickly, we also studied the stability of these solutions. Now we can do what you guys were asking before, which is we can turn on a spectral asymmetry that preserves supersymmetry. And this is, well, I'm parameterizing by psi, but this means that if you want to, well, everything else is determined by this one parameter if you want to preserve supersymmetry. And then you can look at the scaling dimensions of the fermions, and you will find that there is still an instability. There is still a critical E where the solution becomes unstable. But and this is very weird because it would mean that there would be some kind of supersymmetric transition that I'm not sure. Well, I don't know. It would be a little unnatural. But here this lattice-Ward relation resolves this issue. So what we do, that I'm not writing the formula because it's pretty long, but we can derive how the charge of the psi and the chi fermion depend on these spectral asymmetries. And what we find is that the charge of the chi fermion becomes maximal at this point. So then if what you're doing is fixing the charge and increasing it, you won't find any phase transition. You'll just run out of fermions it will just hit the maximal charge. So this one doesn't correspond. There is no phase transition. But we can also turn on charges that don't preserve supersymmetry. And in that case, we expect that there will be similar high to low entropy phase transitions as before. Okay, so that's all. Let me finish with some comments. So we studied the phase structure of n equals 2 SYK at non-zero charge. We found that there are phase transitions to gap low entropy phases. And again, let me emphasize that this is similar to complex SYK, but we have a nice interpretation. And I think, well, okay. We constructed a model with several charges, realizing new types of Schwarzschian theories of strong coupling that could not be realized by the original models. Finally, I try to emphasize the role of index maximization in nearly superconformal quantum mechanics that I think would be nice to understand better. Okay, that's all. Thank you for your attention.
Thank you.
Thank you, Joaquin. So I see that Yanis has his hand raised.
No, it's clapping.
Oh, it's clapping. Sorry, I'm misunderstanding things. Are there some further questions? So maybe I can start the questions. So you mentioned index maximization in 1D. Of course, this also exists as F maximization or C maximization and so on in different dimensions. And you seem to be defining it also in nearly superconformal field theories or quantum mechanics. Do you think this would also extend to higher dimensions, this extremization in nearly conformal theories, nearly superconformal theories?
Yeah, maybe an example is even this paper, because you have a theory that is a superconformal theory in 3D, but then you're looking at it in some states that break the symmetries, and as you go to low temperatures, you will find that some emergent 1D superconformal symmetry that is broken also by the background. So that's dual to the statement that you have a charged black hole, so it breaks the symmetries, but then as you go to near extremality, you develop an ADS2. But the symmetries are also. Yeah, what I'm saying is that maybe you can embed it in a higher dimensional superconformal theory, even if the one that emerges in the IR is broken.
Okay.
But yeah, so that's one example I would like to understand, because there is a clear. Well, yeah, the bad picture tells you that there has to be an emergent 1D near like Schwarzschian mode because of this ADS2 region. So, but but the only thing I don't know is how if there is any way to prove it in general. But
well, that's your job, I guess. This work in progress.
No, this work in progress is even to point this out.
Okay.
Yeah, because also we're also trying to think about if we can figure out how to prove it or maybe apply it to some interesting systems. No, it's just that originally we were just solving the theory at strong coupling and we didn't even think about this issue. So that's why we're trying to analyze it in more detail, and also we can define a lot of. With multiple fermions, you can define a lot of different types of models that have maybe more flavors, and we can check in all of them that this is still true, etc. Yeah.
So is there some JT gravity type description for these supersymmetric SYK models? Or maybe it's well known, I'm just not aware.
Yeah, here it should be, I don't know in detail, but it should be this n equals 2 Sachdev-Ye-Kitaev gravity coupled to a separate U1 supersymmetric theory in ADS2. That where with this extra U1 would correspond to the U1F, to the flavor symmetry, and the R charge would be inside of the JT mode. Yeah. Or if you work in a fixed Q in a fixed flavor charge sector, then it would just be the Schwarzschian, the JT only.
So it would come by reduction of some 4-dimensional supergravity theory on the ADS2 cross S2 horizon, or?
Yeah. For example, well, that's what happens in these cases in ADS4. You have some U1R that you have to determine, and then you have a lot of other symmetries that are there. This model is in a sense a little closer to that. And also in the case of ADS5 cross S5, then you also have a lot of U1s that come from, well, some non-abelian groups that you broke because you put some angular momentum of charges. And then there is only one combination of those U1s that become the one that is inside of the Schwarzschian multiplets. And then you have a lot of other U1s that commute with the supercharge. So that was another motivation for us to study these models. They behave much closer to those examples. Yeah.
Thanks. Are there any further questions? Maybe we can ask them offline to Joaquin. Okay. So let's thank Joaquin again.
Okay. Thank you. Thank you.
And we look forward to Matt's talk next week or next week.
Okay.